Hello everyone. So, welcome to our channel Research Charcha, and myself Suman. And today we have joined by Dr. Narendra Kurra. And hi Narendra.
Hi.
Yeah. So, Dr. Narendra Kurra is currently a assistant professor at Indian Institute of Science and Education and Research, Thiruvananthapuram. And let me his professional career. So he has done his PhD from IISER Bangalore, and after that he has done several postdocs from KOST, Saudi Arabia, as well as Drexel University, USA. And so he is one of the pioneer researcher in the field of energy storage devices, and he has published more than 50 papers, research articles in this line. And today he will be discussing about the on-chip energy storage and current status and future direction. So over to you, Narendra.
Thank you so much for your kind introduction. I see it is echoing.
Okay.
Can you view my screen now?
Yes.
Okay. Thank you, Simon, for your kind introduction. My name is Narendra Kurra. I am currently working as an assistant professor at School of Chemistry, IISER Thiruvananthapuram. Today, I will be discussing about on-chip energy storage, current status and future directions. Here is the background and motivation. Why do we need to develop on-chip energy storage? As we all know that electronic devices are becoming smaller and smaller, which is called miniaturization of electronics. Such miniaturization of electronics demand for development of small-scale energy storage systems. For instance, these small-scale energy storage systems can provide powers in the order of 1 to 100 microwatt, which is sufficient enough to power up some of the small-scale electronic devices including nanorobotics, microelectromechanical systems, remote sensors, wearable electronics, and biosensors, so on and so forth. Also, such kind of small energy storage systems can enable Internet of Things, emerging Internet of Things. This is where there is a huge demand for the development of on-chip energy storage devices. Moreover, they can be compatibly integrated with variety of sensor networks and to develop smart integrated autonomous devices. Okay, let me give you some numbers in terms of the power. As you can see, here is the scale shows the power requirement for variety of personal electronic gadgets ranging from 10 nanowatt to 100 watt. And what we are aiming at through the development of on-chip energy storage devices is to power up some of the personal electronic gadgets which just need around 10 nanowatt to 100 microwatt power. You can see the list of devices that can be powered up using small-scale energy storage systems. If in case you want to expand beyond the scope, it is always possible to expand or enlarge the energy storage systems and then do it needful according to the application requirement. So this is where the on-chip energy storage is going to make huge impact in powering up our personal electronic gadgets. What is the state of the art? Of course, commercially, lithium-ion thin film batteries in the form of micro batteries are very well established in the mature technology available in the literature or in the market. They offer attractive energy density based on the redox chemical reactions. However, because of sluggish diffusion kinetics of the ions, micro batteries suffer from low power density and also limited cycle life. This is where the micro batteries restrict the autonomy of integrated devices. For instance, if there is any bio-implantable chip that is present in the patient body, if battery fails, doctor has to do surgery and then replace it, which is not a good option. So in that scenario, that one would be looking for maintenance-free energy storage solutions. This is where micro supercapacitors find better replacements in place of micro batteries. They offer, of course, attractive pulse powers with like unlimited number of cycle life and fast charge discharge capabilities compared to their sandwich counterparts and excellent rate capability. So this is how the micro supercapacitors they are going to find attractive features when compared to micro batteries for maintenance free energy autonomy devices. So let me tell you something about the basic introduction, how the classification of micro supercapacitors are made in the literature. So there are mainly three main categories. As you can see, the first category as shown here, both positive and negative electrodes with they are in a sandwich geometry with a separator in between, which separates both the positive and negative electrodes electronically, while allowing only passage of ions movement. Of course, the thickness, if you see, it is less than 10 microns. And actually, the name micro comes when the thickness of the electrode material is few microns. That's how the micro, the name, the kind of prefix comes from there, micro supercapacitor. And the second classification comes where you have positive and negative electrodes. They are present on the same plane. This is called interdistated electrode architecture, where these both the positive and negative fingers, they are electronically separated by fixing their distance. Since there is no separator involved here, the ions diffusion pathways can be shortened, which will give rise to higher rate capabilities and power densities in comparison to the sandwich counterparts. And the third category is about developing 3D architectures. Here the thickness can go beyond 10 microns. And the idea of developing 3D architectures is to improve the energy density or the capacitance of the micro supercapacitors by loading active material in a given footprint area. By maximizing the loading of material in a given footprint area, again, there are like many interpenetrating networks, aperiodic structures where cathode and anode with electrolyte embedded together, and such kind of designs need development, need some kind of sophisticated techniques to develop such kind of electrode designs. But today's focus is on talking mostly about interdistated electrode architecture. Suman, everything is going fine?
Yeah, it's fine.
Okay. Okay, let's first take a look at what are the important parameters we need in order to build a micro supercapacitor. So there are mainly four components when you want to build a micro supercapacitor. One needs to have an insulating substrate as shown here. On the top of insulating substrate, we need current collectors. They should be formatted in the form of interdistated design. On top of the current collectors, the active electrode materials will be placed as shown here. And then the fourth component being the electrolyte. If you take overall area of the device, it is typically square millimeter to the square centimeter. So in terms of electrode architecture, there are two main important parameters, that is width of the fingers as well as spacing between the fingers, which is mostly governed by the technique what we use to make this micro supercapacitor. Some of the most commonly employed techniques in the literature include photolithography, laser scribing and laser engraving methods, micromolding, scalpel patterning, and laser writing. So each of the techniques has their own advantages as well as disadvantages. So that some of the techniques I will be mentioning during my talk, like in terms of the processes that involved in developing micro supercapacitors. And coming to the loading of active material, that is called thickness. So here the typical deposition techniques include electrophoretic deposition and then electrochemical deposition methods. Laser scribing is a conversion technique, it's not a deposition technique. Inkjet printing and screen printing, these are the routinely used printing techniques for deposition of active materials. In terms of electrode materials, there are two main classes. Those include carbon materials, which mechanism is based on adsorption and desorption of the charges like ions, electrical double layers, formation of electrical double layers, and also pseudocapacitive materials including metal oxides, sulfides, nitrides, and carbides. The rule of thumb here is that one has to increase the ratio of W by S, that is width to the spacing, so that the equivalent series resistance will be reduced to get maximum energy and power density. And the fourth, the most important parameter here is the ohmic coupling between the current collector and active materials. If you make a sandwich device, it is accompanied by either a coin cell or a Swazelak kind of fixture, where you will have a stack pressure that is available to ensure that there is a ohmic coupling between the current collector and active material. But here, when you take interdistributed architecture, that we are not going to apply any pressure, any stack pressure here while testing the device. So it is very important that the deposition technique itself has to ensure that there is a ohmic coupling between the current collector and active material, so that we don't lose on the power performance of the device. Let me run through some of the very early reports on micro supercapacitors. In fact, those are the triggering points for the many more discoveries or many more like studies that laid out in the literature on micro supercapacitors. So the two key publications came in 2010, exploring on carbon-based materials. This is onion-like carbon, which a typical diameter is around 10 nanometers. So photolithography technique was used to make interdistillated gold electrodes, followed by electrophoretic deposition. These are charged particles so that they can be attracted selectively to the metal fingers. And the main idea of building this micro supercapacitor is the rate capability, that the device was operated until 100 volt per second, which is only feasible having this planar configuration. That is the main idea, that you get enhanced rate capability and power density when you make interdistributed electrode architecture. In a different study, that carbide derived carbon was used as a film, thin film, by sputtering, followed by chlorine etching to selectively remove titanium to get porous carbide derived carbon film here, and then use photolithography to establish interdistributed current collectors, and the device was made. It was published in Science 2010. And there were more efforts in making carbon nanotube graphene carpets using two-step photolithography process followed by chemical vapor deposition. Such devices were employed in AC line filtering applications, which also has high rate capabilities because of open porous structure. And similarly, there was a paper in Nature Communication in 2013 where graphene oxide film was taken and followed by reducing by plasma reduction method at 700C, and then again use photolithography to make graphene based micro supercapacitors. And similarly, that again photolithography combination of spray deposition To avoid the restacking of graphene layers, carbon nanotubes were introduced as a spacer. And some studies you use laser scribing method to directly reduce graphene oxide to reduce graphene oxide, and then graphene oxide in between reduced graphene oxide layer act as a electrolyte, solid electrolyte, to demonstrate this the direct write method here, the capability of direct write method unlike photolithography techniques. And here DVD laser scribing, it's a very scalable process and cost effective process to make micro supercapacitors. And in this work that many graphene based micro supercapacitors have been demonstrated using a simple compact disc or digital video disc laser scribing technique. This is like a highly scalable approach, but the resolution is very poor in such kind of micro supercapacitors. And there are other studies where laser-induced graphitization was exploited in making micro supercapacitor. You start with a polymer which is insulating substrate like Kapton, and like the laser irradiation carbonize and graphitize those irradiated regions into graphitic patterns as shown here, and build micro supercapacitors out of it. So there have been a lot of works on photolithography as well as direct write methods in making micro supercapacitors. Coming to my contributions, that I worked initially on developing conducting polymer micro supercapacitors. Again, I was working at King Abdullah University of Science and Technology. We start with this conventional photolithography approach. Just to give you an idea that we have a substrate like a polyethylene naphthalate. This is a substrate, a plastic substrate. We spin coat the photoresist, and we have a mask which can expose selected regions under UV light, and you have a bond seasoning happens in those exposed regions, followed by development in a developer solutions to remove those exposed regions shown here. And then this is the metallization, where you use titanium as an additional layer and gold as a top layer. So at this stage, one can do lift off, followed by electrodeposition of like polymer, electrochemical deposition using monomer electrolytic bath. But what we found is that since the electric field is enhanced at the edges, we see a lot of deposition happening at the edge of the fingers, and we go beyond certain deposition. We also observe the shorting of the fingers. So this is where what we did instead of doing lift off, without doing lift off process at the stage of C, we have electrodeposited on the entire gold chip. Since the electric field is uniform on the entire substrate, that we get uniform deposition of P dot everywhere across the area exposed to the electrolytic bath. And we performed lift off at this stage. Then we got clean, nice fingers of conducting polymer interdistilled electrodes, followed by placing the gel electrolyte. You can see, like when you do lift off at this stage after the electrodeposition of conducting polymer, and then do lift off, we see there is no extraneous growth at the edges of the fingers. It's only on top of the gold fingers. This will avoid shorting of the fingers and successful fabrication of micro supercapacitors. And this technique was employed to check the frequency response of conducting polymer based micro supercapacitors. And three well-known conducting polymers were chosen: polyethylene dioxythiophene, polypyrrole, and polyaniline. And what we found is that when we look at the phase angle versus frequency response, the P dot micro supercapacitor, the 90-degree phase angle is maintained until 120 Hertz, exhibiting similar frequency response as that of black electrolytic capacitor. In case of polypyrrole and polyaniline, we see that the 90-degree phase angle is maintained up to only 30 Hertz. So which is telling that the redox activity for the polypyrrole and polyaniline is greater compared to P dot polymer. And this is also evidented by doing further analysis from the impedance. by plotting real capacitance and imaginary capacitance versus frequency, where you can where we can see that polyethylene microsupercapacitor has higher capacitance compared to polypyrrole and P dot, whereas P dot operates at a much faster rate compared to the other two conducting polymer based microsupercapacitors because it stores less amount of energy. This is called the maximum of the peak, the frequency you can see. Inverse of frequency is called relaxation time constant, which is high for P dot microsupercapacitor. So this is how we confirm that, the relaxation time constant is low so that you can discharge it fastly. This is how P dot microsupercapacitor operates at a faster rate compared to polyethylene and polypyrrole based microsupercapacitors. In a different work, we were trying to explore the role of current collectors in the design of microsupercapacitors. Our idea is to grow nickel hydroxide material by chemical bath deposition. So we have taken standard metal layer gold, the titanium additional layer and gold as a top layer. When we started doing chemical bath deposition, we didn't observe uniform homogeneous deposition of nickel hydroxide on top of gold. This could be due to the difference in the surface energies of the two materials. And we thought, let's take nickel as a top layer in place of gold. In the attempt to, when we have a nickel, we see homogeneous growth of nickel hydroxide petals as shown here. However, when we started testing in the base electrolyte, potassium hydroxide electrolyte, we see the fingers is getting peeled off. They completely started floating in electrolyte. So this is where we come up with a tri-metal layer approach, where you have titanium as an additional layer in between platinum as a robust material, which is robust enough against corrosive electrolytes and chemically compatible, and nickel as a top layer to ensure the homogeneous decoration of nickel hydroxide petals. So at this stage we were successful, and then we made nickel hydroxide microelectrodes, and we could test the electrochemical performance of nickel hydroxide microelectrodes. Indeed, these devices they can be scanned despite the low electronic conductivity of nickel hydroxide. We were able to run until 50 volt per second. Still we see the preserving of redox peaks even at high scan rates. This is truly due to the geometry, in-plane geometry of nickel hydroxide electrodes, where if you compare sandwich versus planar configuration, that the much more enhanced current values in the case of planar configuration, because the diffusion pathways for the ions is short in the planar configuration compared to the sandwich, where you have the separator is the limitation. So this is going to be a very tedious process that depending on the electrode material, every single time we have to find out the appropriate material for the uniform deposition of electrode materials. So this is where we come up with a universal strategy to develop a universal nucleation layer for development of microsupercapacitors. Here is a scheme shown here. Again, we have this photoresist which was exposed and developed, and then we did metallization, titanium and gold standard. At this stage, we have made this freestanding graphene oxide film, reduced graphene oxide film, on top of a anodic aluminum membrane, and this membrane was dissolved away in base solution. We get the freestanding floating reduced graphene oxide film, which was further transferred onto the on the substrate as shown here. And here now this RGO layer, reduced graphene oxide layer, can act as a nucleating layer for the deposition of a variety of metal oxides, hydroxides, sulfides, even conducting polymers. We have shown that in all the cases we were successful in homogeneous nucleation and further testing of those devices. And this was one of the generic approach we developed in the design of microsupercapacitors. And Okay, not only photolithography techniques, we also developed some unconventional ways of making micro supercapacitors. I'm sure everyone must be using marker pens. The idea of marker pen is that it should be stable against the moisture. When you write something, it should not be erased off in the normal under humid conditions. This is what we take a marker pen and write it on a plastic sheet, and when we dip in water, you see the ink doesn't go off. Whereas when you dip in ethanol, you see ink erases off. There is a solubility contrast between water to the organic solvent. By exploiting this concept, what we have done, we have constructed micro supercapacitors. So here we made this serpentine fashioned ink pattern as shown here. We use roller guide to make like nice written patterns. So this is the ink what we have drawn, and again we do metallization here, like titanium and gold, followed by deposition of active material and then lift off. We get nice interdistated electrodes shown here. The advantage of this technique is that we can also make micro supercapacitors on non-linear surfaces. If you want to perform photolithography, you need to have a flat substrate. Unlike photolithography, limitation of the photolithography here, we have demonstrated you can make on a glass vial, pipe, or cable. And some of the devices, you can see this is a good thing for developing curvilinear energy storage devices. And we have also shown that we can build multi-layers using this approach, and then increase the aerial capacitance of the device. Like as a single stack means one active layer, and bi-stack means you have two active layers with which you can enhance the energy density without compromising the power density. That is the advantage of this unconventional marker pen lithography technique. And further, I moved on to MXenes. MXenes are layered materials. As shown here, this is a well-known example, titanium carbide MXene. You can see here 3 layers of the red ones are titaniums, 3 layers of titanium with sandwiched carbon layers, 2 layers of carbon, and this represents the surface functional groups. We obtain MXenes through wet chemical etching process. During that process, and MXene inherently develops the functional groups such as oxygen, hydroxyl, and fluorine. And because of the negative surface charges on MXenes, they repel from each other, and you can get nice dispersions in water, colloidal dispersions in water. And this material enables solution processing, and it is possible to process them by a variety of spray coating, dip coating, and rod coating methods. And one of the unique properties of MXenes, or even rare properties, it is hydrophilic at being metallic. That is a true advantage of MXene materials. And then we also used variety of techniques as mentioned before: photolithography, laser, and shadow mask, scalpel, and even writing methods to make MXene micro supercapacitors on a variety of substrates. And main applications we show that MXene micro supercapacitors capable of removing AC ripples generated in an electronic circuit. And we show that MXene can be used as transparent conducting electrodes. As you can see here, transparent MXene coating can lit an LED. So in one of the strategies is that since MXene exhibit metallic conductivity, we don't need external metal current collectors. As synthesized MXene has a flake size, lateral dimensions typically 1 to 2 microns. We spray coat large flakes of MXenes, followed by the small flake MXenes, where we probe sonicate MXene solution to get small dimensions around 200 nanometer, which is good for ion diffusion, followed by using laser engraving to make this interdistated electrode architecture, and then placing the gel electrolyte. So this way we develop current collector free MXene micro supercapacitors. And we can fabricate devices on a glass substrate, as well as transfer onto a flexible Scotch tape. Even one can make devices on a printing paper surfaces, so on and so forth. But one of the key applications of MXenes, because of their high conductivity and excellent charge storage properties, they can be used in like electronic circuitry to remove the ripples that produced in an electronic circuit in ICs, integrated chips. So this is a bulky electrolytic capacitor, as you can see here. This is one of the bulkiest component that is hiding or sitting in the circuit board. It has a low energy density. If we can make a supercapacitor that is operating at high frequencies, one can get rid of this bulky capacitor. This is where one of the key applications of micro supercapacitors fit in. And in our study, we have shown that using photolithography and spray coating method, on 8-inch silicon wafer, we could make 100 devices of MXene micro supercapacitors. And when we check their phase angle versus frequency response, you can see the phase angle 90 degree is almost being maintained until 120 hertz. That is a requirement for AC line filtering of 120 hertz signal. And this can be operated at a very high scan rate, that is like 300 volt per second. And in terms of capacitance at 120 hertz, it's around 30 farad per cubic centimeter, and which give rise to the energy densities much higher than bulky electrolytic capacitors. So this is where MXene micro supercapacitors can fit and compatibly integrated with the electronic circuits for AC line filtering applications. And also, given the tunability of rheological properties of MXenes, we can develop MXene inks, and they can be readily filled into the pens to make MXene pens. And when you write something, it is like these are conductive, MXene patterns. And of course, the ink characteristics are such a way that even we can replicate fine features. And then this is the main the advantage that that the rheological properties of MXene ink enables us to make fine features without smearing effects. And again, we can also demonstrate that we can directly write or make devices on a curved surfaces, because it's a single step process. And series connected device can lit an LED, can act like a micro power source. And one of the technique we developed at Drexel is called automated scalpel. So we obtain transparent MXene coatings by dip coating method. So this is a MXene colloidal solution, dip coated glass was dip coated in this colloidal solution to make semi-transparent coatings, followed by engraving using a scalpel method to make these interdistricated electrodes. If this thin film has to be taken through the photolithography process, probably at the end of the photolithography, we may not end up having this film, or the intrinsic properties might be affected by the residual photoresist. This is where direct write techniques, they have a unique advantage to faithfully retain the intrinsic properties of MXene films for energy storage, transparent energy storage applications. With this, I just summarized the works what we have done besides the literature reports on micro supercapacitors. Regarding future research directions, this micro supercapacitors, since the charge always varies linearly with the potential, so one has to power them up using some energy harvesting units. And this is where some efforts actually they focused on integrating with the triboelectric generators or piezoelectric generators, where mechanical motions they produce voltages, and then those voltages can be fed in to charge the micro supercapacitor. Some of the demonstrations have been done already in the literature, and one of the crucial things about micro supercapacitors is the self-discharge behavior. When you charge a supercapacitor, it is always in its high free energy state, and by thermodynamic driving force, based on the self-discharge process, the charge will not be holded, unlike in the case of micro batteries. So one has to slow down the self-discharge kinetics of micro supercapacitors in order to use them effectively for some applications. And again, in the literature, mostly the fabrications methodologies and development of electrode materials and their electrochemical performance have been demonstrated. But for the real life applications, the packaging and the usage of devices is very much required to show the sustainable and maintenance free operation. And the concepts where the 3D designs are evolving, one wants to have increase the loading of active material in a given footprint area without compromising on the power performance. This is where the 3D micro supercapacitors are being developed, where the 2D micro supercapacitors, they have a limited energy densities. That is the main reason. And some of the directions in the recent papers focusing on developing on-chip metal ion hybrid capacitors, where instead of exploiting the symmetric two electrodes, one can have an EDLC type electrode as one finger, an intercalative type of electrode as the opposite finger. And since when you have an asymmetric design, you can have maximum voltage, and hence E is equal to half CV square. One can increase the energy density significantly by adopting on-chip metal ion hybrid capacitors. The power performance will be maintained by the porous carbon electrode, and the energy density will be improved through the intercalating electrode that is being used in the design of on-chip metal ion hybrid capacitors. So the ultimate goal is that all these micro supercapacitors developments and packaging, integrating the devices, 3D concepts, and even on-chip metal and hybrid capacitors, they should be capable of powering up small-scale sensors and networks. This is very much required in the future, especially like you want to have environmental monitoring, where you need energy autonomy of the device, which is capable of monitoring the changes in the environment, which can sense gases in the environment, such as oxides of carbon, oxides of sulfur. And those devices need to be powered up in a maintenance free. This is where micro supercapacitors will be the best choice. And similarly, when you have in a factory monitoring and also agricultural management, many fields do require different type of sensors, and those sensors and networks, and again the sensor senses it and then sends the signals to the receiver, and then you get the data, and based on that you will monitor it. So this is where that the integration among various components, sensors and networks, is very much required. And the micro scale energy storage devices, especially micro supercapacitors, they offer maintenance free solutions and supply enough power for the successful operation of the sensors and network units, so that we are in a position to monitor them effectively and take the necessary preventive measures in this regard. So this is where the future is going to be, that one has to fix all the problems with micro supercapacitors and try to develop an energy autonomy for the integrated sensor network devices. With this, I would like to thank many students, like undergrads, grads, and master students who I worked with at Drexel and KAUST team members. Professor Yuri Gagotsi, who was my postdoctoral mentor at Drexel University. Professor Usam Al Sharif at KAUST. Thank you so much for their help and support during my postdoctoral tenure. Thank you for your kind attention. I'm happy to take any questions if you have.
Yeah, thank you, Narendra, for your wonderful talk. So,
thank you so much.
It is exciting to see that such a simple methods are being used in your work to fabricate this high performance and cutting edge energy storing devices. And let me tell you that I am also working on this field, and I closely follow your work. And when I read about that marker pen lithography, that paper, so that was really exciting for me to that such a simple method can be used to make the micro supercapacitor devices. This is very simple and means simple method to use.
Yeah.
So that's what I understand. So I have few questions regarding your talk.
Sure.
So first question is that what many people ask that. So are the supercapacitors are going to replace the batteries, or batteries will be there, or the supercapacitor will be then aside? Means how it is going to be in the future?
Yeah, my answer to this question, certainly supercapacitors cannot replace batteries, but supercapacitors do replace batteries when there is a low energy requirement for high power applications. Let's say for a particular application, you need low energy density requirement. It's typically less than 10 watt hour per kilogram, but you need supply of very high power, like up to the order of 10 kilowatt per kilogram. This is where supercapacitors are the best bet over the batteries. In some of the applications, that both supercapacitors and batteries can be used in tandem, so that the cycle life of battery cannot be compromised by operating them in the high power mode. So the very clear answer is that for high power applications, supercapacitors are the best choice. Definitely batteries are not going to be operated. The second is that use them in tandem for some applications where you want to last for a long time, but at a high power density.
Okay. So as you have already told that, so what do you see? Means where do you see that after 20 years or 25 years in the future? So how the research on the supercapacitor field will be? Means in what direction it will be?
So you are asking about research on supercapacitors.
Yes, micro supercapacitors maybe. Supercapacitors, micro supercapacitors.
Yeah, these two are like two different things. Like if you talk about bulk supercapacitors, and right now, like you, as you know, that carbon-based materials have been exploited already, and they're typically tuning the pore size and surface area. All those parameters have been optimized. And now current technology, they can provide until 10 watt hour per kilogram commercial electrical double layer capacitors. And now the direction is going towards pseudo-capacitor materials, where you have fast surface redox reactions. You want to achieve simultaneously high energy density as well as high power density. For instance, MXenes are one of the key materials for developing fast charging devices and developing hybrid energy storage devices, where you combine a pseudo-capacitor material with electrical double layer material to build a hybrid device which can have simultaneously high energy and high power densities. Okay, this is where mainly the supercapacitors, I mean, going beyond carbon materials, like going into the pseudo-capacitor materials in terms of devices, moving into the hybrid concept.
Okay.
This is where the main research is going to be.
Okay. So one means the next question is that what kind of electrode material is required for the supercapacitors? And the extension of this question is that, as you have already told that you have used carbon-based materials and MXenes as well to make the electrodes. So I just want you to tell that among these two materials, so which one can perform better, carbon or MXene?
Yes, so there are, like for supercapacitors, there are variety of performance metrics. When you look at only like when you look at in terms of capacitance, energy density, of course, MXenes are the better choice. MXenes outperform carbon materials because of redox charge storage capability of MXenes over carbon-based materials. But when you look at the cycling stability, long-term cycling stability, carbon materials are the best choice over MXenes. When you look at the cost wise, the carbon materials are pretty cheap compared to MXenes. So these are the main different, like if industry they want to make a technology out of MXenes, supercapacitors, definitely right now the cost is very high. They're not going to use MXenes for instance. But for micro supercapacitor application where you require small amount of material, even though cost is high, MXenes can be employed in supercapacitor, micro supercapacitor applications. They perform very well compared to carbon-based materials. So this is where like each of their material has own advantages and disadvantages. And then MXenes can be used effectively in asymmetric configuration, where the cycling stability of the devices or some cycling stability of MXenes can be improved by using them in asymmetric configurations.
Okay.
And the main requirement for any general rule for electrode material that it should have a high surface area, good electronic and ionic conductivity, and it should be corrosive resist. It should be it should tolerate the corrosion against aqueous and organic media, and you should have like it should be cheap. Another requirement is it should be a cheap available material. And it could tolerate potentials like that's what I told, electrical corrosion, electrochemical corrosion events and all. It should be robust against all those electrical reactions.
Okay. So my next question is that what kind of electrolyte is preferred in this one-chip energy storage devices?
Yes, I think the reason, the answer here is the gel electrolyte or solid electrolytes are preferred because they don't have leakage issues. But in the laboratory testing setup, we always do it in the liquid electrolytes in order to see how far it can work. Again, you have the solid electrolytes, the limitations with the power density. But in the when you look at the commercial point of view, packaging wise, the solid electrolytes are going to be the best choice, and one has to develop solid electrolytes with ionic conductivity same as that of liquid counterparts.
Several questions like in your one of the work you have shown that the PE dot was working better than the pani and polypropylene. So why is that? Polypyrrole, sorry.
Yeah, so it is based on the redox activity. If you take P dot, even if you test it as an electrode material, which shows much lower capacitance capacity compared to polyaniline and polypyrrole. This is to do with the doping, the amount of doping that it can take up in order to show the redox activity. So if you look at P dot, it is only 0.33 in comparison to 0.5 or around 0.6 for polypyrrole and P dot. That actually the doping decides the capacity of the material, and the multiple redox states are available for P dot, polyaniline compared to P dot.
Okay. And one of the work you have shown that for the nickel hydroxide,
yes.
So there in the cyclic voltammetric curve, there is a huge pseudo capacity peaks are coming.
Yeah.
So do you term these devices in a supercapacitor or as a battery?
Yeah, when you are referring to a device, in the device, either you can call it as a supercapacitor or battery. For a device, there is no term called pseudo capacitor. The pseudo capacitor term is applicable to the material itself. That when you say a material is exhibiting pseudo capacitive characteristics, even though it undergoes redox reactions, but the kinetics of the charge storage process are same that of capacitive type of electrodes. So this is where the pseudo capacitive nomenclature comes into picture. In the nickel hydroxide case, So we call it as pseudocapacitive. That was a kind of misclassification, but we were thinking that in terms of the power, like we were able to operate at very high scan rates, similar to that of a capacitor type of technology. At the time, there were no guidelines we found in the literature about the proper appropriate classification. And after we published that paper, we saw a couple of papers published in the literature discussing about the appropriate classification, that when to call a material pseudocapacitive, when not to call a material pseudocapacitive. And in the device configuration, you should not use a term called pseudocapacitive. So this is where, we found it. And again, at that time, our intention was to deliver that these nickel hydroxide electrodes can be operated at very high scan rates. That means the power performance similar to that of capacitor type of electrodes. That's why we named it as pseudocapacitive, but that was not correct.
Okay. So your video is not coming. So is there any problem?
My video is not coming. How come?
Your face is not visible here. Your voice is visible. It's audible.
What about now? Can you see me now?
No, still you're.
I can see myself.
Yes, but here in my computer it is not coming. Okay.
Okay, maybe stop presenting. Can you see it now?
Yes, I can see.
Okay.
I can see. So my last question actually.
Sure.
So what are the main differences between the research environment in India and as you have worked in the other developed countries and good universities in outside in the foreign countries? So what do you feel that what are the main differences in India and there?
It's a very difficult question, but I will answer whatever my observations I have done. So the main difference comes between India and developed countries, the kind of organization. Like in developed countries, we find many postdoctoral researchers who always help graduate students to progress very well. And you have many collaborative efforts that happens in developed countries. This is where they end up publishing high quality papers. And somehow in India, not many collaborative efforts are, taken, here seriously. And we tended to show as an individual, we want to perform better at the compromising quality of publications. And there it is like there will be a lot of freedom and flexibility given in the developed countries. Absolutely, it is a true pleasure to work there. And once you have the freedom and flexibility, you can get the innovation or creativity from the individual researcher. And that's how they extract maximum out of a researcher. And there they don't mix up personal and professional life. But those are the few important things I observed in developed countries. This is where some of the things we can adopt to further advance in the science and do better science in India.
Yes. Yeah. Thank you, Narendra, and once again for your wonderful conversation today. And
Pleasure.
Thank you joining us in our channel. And to our viewers, if you have any queries, so you can directly ask to Dr. Narendra Kurra. So his email ID is given below. And also, please share and subscribe to our channel Research Charcha. And stay tuned for more research updates in our channel. Thank you. And bye,
Thank you so
Narendra.
much. Thank you so much. Good night.
Good night. Bye, everyone.